So we want to find, the first step is we want to find a differential equation in V. We have a couple of relationships here, right? We've got the constitutive relationship for a resistor versus I, and that's V sub R equals, what is it, Jonathan, for Ohm's law? V sub R equals
I times R.
I times R. And there's our I, and there's our, and we know what our R is. We've got one other constitutive relationship. A constitutive relationship, again, is the relationship between current and voltage. And we've got this capacitor in there. So Jack, tell me, what is it for, what's the constitutive relationship that relates current and voltage for a capacitor? And I'll start you out. It's I equals.
Then I equals 1 over the like weird little T looking thing.
The other way around. I equals C times.
Oh, the derivative of V.
The derivative of the voltage across it. That's it. That's it. Okay. So we're going to derive our differential equation using these rules. And because all these components are in a series, we're going to use KVL to start us off. So by KVL, we can sum up our voltages going up here. So minus our V plus our V sub R has got to be 0. And now we can just substitute things in the top. Let's substitute in, by the way, this is our circuit geometry. I don't care if it was a capacitor and a resistor, or a capacitor and an inductor, or my grandmother and a resistor. It's going to be V across minus V across grandmother plus V sub R equals 0. It doesn't matter what the components are, it just matters how they're connected. And if they're in series, the sum of these voltages have to be 0. Now we're going to talk about, now we're going to add in the equations of what they actually do, the constitutive equations to the geometry. So adding in these constitutive relationships, we can see that V sub R is equal to I sub R. And so that adds in the resistor value. And we've got this, now we need to somehow add in what the capacitor does. And we see an I up here. So we're going to add that in too. That I is equal to C, BC prime, R equals 0. And so that's adding in our C. And now we've talked about both the geometry of the circuit. We've put in our constitutive relationships for our components. So that's got to be a complete defined differential equation. It's just not in the usual way we write them. The usual way that we would write these differential equations is to say, oh, hey, take a look, this V sub C, that's the same thing as just V, the way we've defined it. So we can write it like this. And the way that we usually write a differential equation is to write the V prime first, and to get that V prime alone. So we'll divide by RC. And so now we've got the first part of our struggle to solve this using differential equations. We've written the differential equation that describes voltage for it. And those of you who have finished differential equations know that you need to have, Kyle, you finished differential equations. What's one extra thing do you need to solve a differential equation besides the equation itself? As it stands, this will give rise to a whole family of possible solutions. So what will give us just a single solution?
You need your initial condition.
That's it. Perfect. And our initial condition is V at 0 is equal to capital V naught. Beautiful. All right. We've got the entire differential equation worked out. Let's now solve it. And then once we solve it, you'll never have to do this again. You can just use the results of our solution. So we're going to have to solve it. You know that there's a natural part of the solution, and there's going to be a forced part of the solution. And then there's a total part of the solution. which is just the natural part plus the forced part. So the natural part, we put in a S wherever we see a derivative. So there's the derivative. No derivative here, so that's just times 1, and that equals 0. Therefore, our S, we solve for S and we get it's equal to 1 over R. We get 1 over RC. Let me just really quick check to make sure I made no errors. This is a really subtle error, and it came right in this spot, right here. So it's true. These two things are true. But take a look at how I've defined these components. This is only true, and this is only true for passive sign convention. And passive sign convention says, if here's your component, and you've got current going into it, we always define according to passive sign convention, the current, the voltage being more positive where it enters and it more negative when we leave. And this again is true for any component at all. This is what passive sign convention is. So I did not do that up here. Here, R and I works, but take a look at this I direction versus the voltage across the capacitor. Here we've defined it the opposite way, that the voltage is more negative entering and more positive exiting. So if that's the case, I have to flip the sign. Now, this is a correct statement, but right here, the relationship between the current and the C dV dt has got to be a minus plus a negative in here in order to make this current that we're considering work in the opposite direction for the capacitor. Is anyone unclear about that? That's a really subtle thing that probably was not a big deal in circuits 1, but will become a big deal in circuits 2. That the constitutive relationships assume a passive sign convention. So if you're not going to use a passive sign convention, you got to have a different, you've got to put a negative in one of these things, in front of one of these things. Questions on that?
Colonel McCormick done that a lot last year.
Say it again.
Colonel McCormick harped on that a lot this year.
Oh, that's awesome. That's awesome. Because if I had been listening to Colonel McCormick, I wouldn't have made that mistake. I'd have thrown a minus inside here, which would have then changed this to a positive. All right, which makes this a positive, and which makes this S equal to minus 1 over RC. All right, and now things work out. Now our V net from these two things, we know our V natural of T has to be equal to any constant times E to the minus 1 over RC times T. So this is the root of S. And so now this is our natural solution. And the cool part about this is that if you plug that into here, no matter what your K is, K can be +1, -20, 3 pi over 2, it will satisfy this equation. So now we just need to find out what K is. But before we find out what K is, we've got to solve for the force part. And the force part is a particular solution that yields the right side. Well, if the right side is 0, by inspection, the force part will be 0. And so the total is going to be V is equal to K e to the minus 1 over RC times T. We substitute in our initial condition, V of 0. We said is equal to V sub naught is equal to K. And then, Will, what is this over here when we substitute in 0 for T?
That's going to just go to 0 up top, which would pull everything to 1.
That's it. That's exactly right. So it's times 1. So therefore, K equals V sub naught. And therefore, the total solution is the voltage across the capacitor for any time greater than 0, we're only examining it for greater than 0, is equal to our initial condition times e to the minus 1 over RC times T. And that is almost the way it's typically written in electrical engineering. In electrical engineering, we create this new variable, though, tau, which we say is equal to R times C. And this is the solution that we're looking for. And now that we've derived it, you can just plug that in whenever you need it. This R times C is something kind of special. We call RC the time constant. And it has units of seconds, which if you think about it is kind of mind expanding. It means that multiplying ohms times farads has units of seconds. There's your plug and chug. That mistake that I made about the direction of V and I, that was an honest mistake that I did, but I'm very glad I made it because it points out how easy and subtle it is to make those mistakes.